Here are some examples that I didn't have time to cover in class, so I'm making a video for you to watch. Question 17 says in the figure, in part A, this figure, particle 1 and 2 have charge 20 microcoulomb and are held at separation distance of 1.5 meters. What is the magnitude of the electrostatic force on particle 1 due to particle 2? In figure B, particle 3 of charge 20 microcoulomb, the same as those two, is positioned as to complete an equilateral triangle. What is the magnitude of the net electrostatic force on particle 1 due to particles 2 and 3? In part A, it is simple. Fa is kq squared over d squared, so we call it Fa. In part B, we have an equilateral triangle, and so we need to find the net force on this one that's up here due to these two. The force of this third one is this way, and it has the same magnitude as Fa, so we call it just Fa. The other force is also the same magnitude, so that is also Fa. But you see that if you put a coordinate system here, the x components, the horizontal components, cancel each other. The vertical components add up, and because of symmetry, they're both the same. So the net force will be twice the y component. So F in part B becomes twice the Fa y component. The two y components of each one becomes the total force. All right, but what is Fay, the y component of Fa? That would be Fa magnitude times sine of 60 degrees, this angle. Sine of 60 is square root of 3 over 2. So 2 cancels, you get square root of 3 times Fa. In other words, the force in part B is square root of 3 times the force in part A. So if you put the numbers in for Fa, you have K q squared divided by d squared. D is 1.5 meters. So that turns out to be 1.6 Newton. And in part B, square root of 3 times, that becomes 2.77 Newton. So that's this problem. In this problem, it says in the figure A, 3 positively charged particles are fixed on an x-axis. Particles B and C are so close to each other that they can be considered to be at the same distance from particle A. The net force on particle A due to particles B and C is 2.014 times 10 to the negative 23 Newton in the negative direction of the x-axis. In figure B, particle B has been moved to the opposite side of A, but still at the same distance from particle A. The net force on A is now 2.877 times 10 to the negative 24th Newton in the negative direction of the x-axis. What is the ratio QC over QB? So they are all positively charged, means that these two are applying repulsive force to the negative x direction, so they add up in here. But because in this case, also the negative direction of x-axis means that C must be bigger than B. So the forces are like this. In this case, they add to each other. In this case, they subtract, but the force of C is bigger. So if you write down the equations in part A, net force will be K QA QB, the force of B on A, divided by R squared, whatever that is, plus K QA QC, the force of C on A, divided by R squared is this. And sum of those two gives this number, which is 2.014 times 10 to the negative 23. And in part B, we have the force of C minus force of B, KQAQC over R squared minus KQAQB over R squared equal to 0.2877 times 10 to the negative 23. So you see that I wrote as a power 10 to the negative 23, so that we have the same power here. And now, because of R is not given and QA is not given, we can factor these values. So it becomes KQA over R squared, which is a common factor, times QB plus QC. And here becomes KQA over R squared times QC minus QB, becomes like that. So now if we divide these two equations, all these unknown numbers will cancel out, and 10 to negative 23 also cancel out. So we have QB plus QC divided by QC minus QB equal to this 2.014 divided by 0.2877. And this turns out to be about 7. And because we're looking for the ratio of QC over QB, we can divide both numerator and denominator of this fraction by QB. So what we get is 1 plus QC over QB divided by QC over QB minus 1 equal to 7. And then we can call this QC over QB alpha to just make it look simpler. 7 alpha minus 7 is equal to 1 plus alpha. So this is the equation that we get from here. And now if we move this alpha over, we get 6 alpha, move this 7 over, becomes 8. So 6 alpha becomes 8. So alpha becomes 8 over 6 or 4 over 3. So the answer is QC over QB is 4/3. And as we expect, QC is larger than QB because the fraction is bigger. All right, so this is question 18. In question 23, it says particles 1 and 2 of charge 3.2 times 10 to negative 19 Coulomb are on a y-axis at distance d 17 centimeter from the origin. Particle 3 of charge q3, which is 6.4 times 10 to negative 19 Coulomb, is moved gradually along the x-axis from x equal to 0, means here, to x equal to 5 meters. 5 meters is much bigger than this d, so basically move to infinity. At what values of x will the magnitude of the electrostatic force on the third particle from the other two particles be minimum, maximum, and what are the minimum and maximum values? First of all, you know that when x is equal to 0, particle 1 applies a downward force on particle 3, particle 2 the same upward force, so they cancel each other. So the minimum for part A will be 0 and at x equal to 0. The minimum is clear at this 0 point, but there's a maximum somewhere. How do we find the maximum? We're going to do that. First, we need to find the net force with respect to x. Let's say the distance is x, and in terms of x, what is the net force? That's what we are going to do. First, this particle 2 applies a force on particle 3 because it is repulsive, it will be this way. Particle 1 applies a force, it is along this direction, this way because it's repulsive. So these two forces are adding up. The angle here we call alpha, which is the same as the other angle here. So F13 is KQ1Q3 over R squared, which is KQ1Q3 divided by R is this distance. So R squared is X squared plus D squared. So we call it just F1. F23 is KQ2Q3 divided by R squared, the same R. So KQ2Q3 divided by X squared plus D squared, which we call F2, which is the same as F1 because the charges are the same. So the magnitude of the net force is the magnitude F, which is 2 times F1 times cosine of alpha. You see, this is the y components cancel each other, the x components add up. So we get twice the x component of one of them, and that would be the magnitude of one of them times cosine of this angle alpha, which is the same as this angle alpha. So what is cosine of alpha? Cosine of alpha is adjacent over hypotenuse. Adjacent is x, hypotenuse is a square root of x squared plus d squared. And that becomes f equal to 2k q1 q3 over x squared plus d squared. That's f1. 2 times f1 times cosine of alpha. So this is the net force. And this x squared plus d squared has a power 1 here and 1/2. you can combine it and make it power 3 half. And 2k q1 q3 times x goes on the numerator. So this is the net force, and it depends on x. As you expect, when you put x equal to 0, this becomes 0. And when x goes to infinity, it means you go far, far away from these two charges, then x increases by the third power in the denominator, but in the first power in the numerator, the force dies out by the inverse square law, which is what is expected. Now the question is, at what value of x we have maximum force? All right, so this force goes from 0, goes to non-zero, and then goes back to asymptotically, of course, goes to 0. So the question is, where is, at what x this f becomes maximum? As you know from calculus, in order to find the maximum value of a function, we set the derivative of that function with respect to the variable equal to 0. So we need to take the derivative of f with respect to x and set it equal to 0 and then solve for x. In order to do that, it is better to write this denominator to the power 3 half, bring it up and write it as a power of negative 3 half. So the expression becomes 2k q1 q3 x times x squared plus d squared to the power negative 3 half. Because we're going to do derivative, this is easier. So we set df over dx equal to 0. So what is the derivative of f with respect to x? This is a product. These are all constants. 2k q1 q3 is all constant. Is a product of x and this expression of x. So we use product rule, so derivative of x times that plus derivative of this times x. So that would be derivative of x is 1 times the rest of it, 2k q1 q3 x squared plus d squared to the power negative 3 half, plus derivative of the rest times x. So derivative of this expression is negative 3 half, that's negative 3 half, times the expression to the power 1 less, negative 3 half minus 1, times the derivative of what is inside from chain rule. That would be 2x. And then times the rest of it, which is 2k q1 q3 times x. So this is the derivative of the whole thing, and we set that equal to 0. So as you see, 2k q1 q3 can be canceled, and this 2 cancels this 2. So first we cancel that, cancel these 2's, and cancel that. And then if you multiply by x squared plus d squared to the power 5 half, this becomes the x squared plus d squared. This goes away, and you can move it over, it becomes 3x squared. So it becomes like this, x squared plus d squared equals to 3x squared. And then you can solve for x. You bring this over, you get 2x squared equal to d squared. So x squared becomes d squared over 2, or x becomes d over square root of 2. All right, so at this point, what this means, the derivative at this point, at x equal to d over square root of 2, the derivative is 0, means that at this x equal to d over square root of 2, we have maximum for the force. So we have this force value, which has the expression in terms of x, and for maximum we have x equal to that. We can then put x equal to this value and calculate the force for what is the maximum force, maximum magnitude of force. So here we get 2k q1 q3. Instead of x, I put d over square root of 2. X squared becomes d squared over 2 plus d squared. And then d squared factors here becomes d squared to the power 3 half becomes d cubed. And then we have 3 half to the power 3 half. And you have d over the square root of 2 here. Now one of these cancels, and this square root of 2 multiplies here. You have 1 over 2 to the power 3 half and 2 to the power 1 half. So we get the power 1/2 to the power 1. That multiplies by this 2 becomes 2 squared. KQ1, Q3. One of these canceled, it goes away in the numerator. And then we have 3 to the power 3/2. So this maximum force is this. You can put the numbers, that's not important very much. You can put the numbers now in and calculate the maximum force. All right, I think that's it. And I hope you enjoyed that. Have a good day.